Let's see, where's my notes? Over here. Okay. So that basically explains what top-down design is and the rationale of top-down design. It's just, that people cannot deal with a lot of details all at the same time. Now, the other thing you have to remember is you also have physical limitations, not just mental limitations as to how many things you can keep track of, but also how many things can be displayed on your screen when you when you read your programs. Okay? Let's say you have a pretty high-resolution screen, 1080p. 1080p means that the vertical resolution is at least 1080 pixels, which is pretty good. I mean, that's a pretty high-resolution monitor. If you use a smaller font, how many lines of text can you fit on a screen phone? A lot. Okay. I can demonstrate how much you can fit because I personally like smaller fonts, so I can show you exactly how many we can fit here. So this will require me to switch the monitor back to its native resolution. We'll switch. Oh, I cannot do that because if I did that, the screen recorder will probably get confused. So I really should not be doing that. We can do it by calculations. We have 1080 pixels vertically. Okay, how many pixels do you think a line would have to take up using the smallest legible font?
10 or 9.
About 10. 10 pixels. Would make for pretty much the tiniest font you can actually deal with. Realistic case. So we divide it by 10, we get 108. In other words, if you open up one text editor and stretch it out as far as you can vertically, and use the smallest font that you can pick up, which takes up about 10 pixels per line, you will be able to fit about 108 lines in the editor. In other words, you can display about 100 lines for each screen. Is that okay so far? I have seen subroutines. Okay, we haven't talked about subroutines yet, but you can look at a subroutine as a unit of algorithms. I have seen subroutines that are in the order of 500 and 600 lines. Okay, let's think about it again. Okay, a single piece of pseudocode, not pseudocode in this case, it's actually C code, but a single piece of algorithm is going to be like 500 lines. I have to use page up and page down in order to locate the beginning or the end of a particular construct, because it will span across more than 100 lines. Why is that a bad thing?
Can't remember.
It's really hard to line things up. Okay, even assuming the program uses the correct indentation. Remember the importance of indentation. We can put a ruler next to it and easily locate the beginning and the end. What if it's scrolled off the screen already? Then your ruler is not going to be very helpful, is it? Okay. So in those cases, what do we have to do? Yep.
There are on-screen rulers that can basically it'll show you this line is say 3 inches in. You can scroll down and then click that one.
Yeah, you can do that, or can print it out. Okay. In the good old days, we have those fan fold paper. Do you guys know what is a fan folded? What is fan folded paper? So with fan folded paper, it's one continuous sheet. If you have like a 3,000 line program or 3,000 line algorithm, you can just print it out on one single, continuous piece of paper. Then you can actually sit down and use a ruler to line up stuff to try to see if you can find the beginning and the end of anything. Okay? In the good old days, they don't have any lasers, right? So it's really hard to line things up because you can't find a ruler long enough to help you line it up. Now these days, because of lasers for all kinds of tools, they can project a straight line on a piece of paper or anything that's reflective. Well, not infinitely. The signal strength does decrease over distance, but it'll be easy to line up. But you guys get the idea. It is really hard to debug any program that is too long, because it won't fit on one screenful. So as a general rule, okay, this is not something that you'll be graded on, just a suggestion. In any programming class, do not write subroutines or any single piece of code that will span more than one page. Because anytime you have to span more than one page, it gets really hard to see both the beginning and the end of the higher level, constructs. Okay, so that's the other reason why we need top-down design. Because how much logic do you think I can fit in 108 lines?
Quite a bit.
Quite a bit, and yet not enough. Can I write Microsoft Word in 108 lines?
No.
There you go. That's my point. Okay, so you have to use top-down design. So we have just covered 3.1 and 3.2. 3.1 talks about algorithm specific considerations, which has to do with the number of lines you can display on each screen and why it is not a good idea to exceed that many lines when you specify a single algorithm. 3.2 talks about if we can only fit 100 lines on the screen and Microsoft Word or some major application program has to be longer than 100 lines, how do we do it? Well, we use top-down design. In other words, one line of those 108 lines may just specify, I want to do this operation, but without actually spelling out how to do that operation. Okay, let me say that again. Top-down design means, within these lines, these 108 lines or whatever, 160 or whatever lines, one line may not actually tell me how something is done. It simply tells me what needs to be done by the time I get to that line. Okay, so this is a good lead-in to subroutines later on. So we'll just remember this is a good lead-in to subroutines. If you want to go back to the Google Map analogy, basically if you look at Nevada here, it is a single line of that 100-line program. It does not display all the details of Nevada. It simply tells me that Nevada is here. It is next to Idaho, Oregon, California, Utah, and Arizona. Okay? It's the same thing with top-down design in terms of programming. A line may not tell you all the details of how to do something. It simply says, this has to be done after this, but before this, and you should only do it if this condition is true. Okay? It's hiding details from you. Okay? Any questions at this point about 3.1 and 3.2? No questions? So 3.3 starts to become a little bit more interesting because I'm using a specific example to illustrate top-down design. It has to do with factoring. So before we move in and actually talk about factoring, let's see if we know and still remember how to do factoring. I'm hoping that most of you are comfortable with factoring. Yes, it is more math stuff, but this stuff, really, you guys should still remember how to do. Okay. If I want to factor, let's say, 72, how can I factor 72 into all prime factors?
36 and 2.
Okay, so we pick 2 first, because it is quite obvious that 72 is divisible by 2. So we say 72 is 2 times 36. So now I look at 36. Can I factor 36 into its prime components?
You can divide it by 2 again.
Okay, so it becomes 2 times 18. I look at 18.
Divided by 2.
Okay, I look at 9.
3 times 3.
Okay, I look at 3.
3 times
And you're stuck.
Oh, okay, well, 3 is 3 times 1. I'm
Yeah.
done. Okay, and I look at 1. By the way, is 1 a prime number?
Yes.
No. 1 is not a prime number by definition. Okay? Go to Wikipedia, go to your math book, but they will define a prime number as any number that is divisible by 1 and itself, and it cannot be 1. Okay? So 1 is not a prime number.
I think that's silly.
It is not silly because it has to do with how they apply that definition of prime numbers in different types of math. So making it like this makes it easier to say, prime numbers will have these properties instead of saying prime numbers except 1 have these properties. So they have to exclude 1 because 1 is always the exception of the rule when you want to describe prime numbers in equations and other theories. Okay, so I think we have a pretty good idea of how to chop a number down into its prime components, right? Well, let's look at another number. Let's look at let's see, that would be too obvious. That would not be so obvious. Okay, let's find out the prime factors of this number. And you guys would go like, are you serious, Tech? This is a waste of time. I mean, we're supposed to be learning algorithms, not how to factor big, insane, huge numbers. But I'm making a point here. I'm making a point here because if I want you to list all the prime factors of this, some insane number, it will be pretty difficult. Unless I can tell you and say, oh, ask Joe. Joe is an expert of finding prime factors of a number. Okay, so your job is now a whole lot easier, right? Because your job is to list all the prime factors. But since Joe is really good at finding a prime factor, you can just say, hey, Joe, what is the prime factor of this number? Joe will return with a number, and you say, okay, one of the prime factor is blah, 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 and the remaining portion is going to be, whatever is the quotient of the division, and you move it on to the next line. And on the next line, what do? You ask Joe again. Okay? So that makes your job a whole lot easier because Joe can deal with a subtask of factoring a number. Is that making any sense? Okay. So it is the same thing in programming. If I can just say on one line, instead of spelling out how to find a prime factor given a number, instead of spelling out how it is done, and I can just say, this line does that magically. That makes my algorithm a whole lot easier to express, don't you think? Okay? Yep.
Are you talking about recursion?
No. Has nothing to do with recursion.
Okay.
Yep. We cannot talk about recursion until we talk about subroutines. Okay. So the whole idea is now I can write my algorithm a whole lot easier. So let's go ahead and try to write an algorithm to factor a number into its prime components. Okay. How many people think that this probably is a loop because we don't know how many times we have to perform the operations? Probably a loop because I didn't tell you the number, the range of the number. So for sure we know this is some kind of a loop. So what I'm going to do here is I'm using different versions. I'm using, okay, let me just use a horizontal bar to represent it. Okay, version 1. Version 1 is we have a loop of some kind. We don't know what is inside the loop. This is not a new kind of loop. This is a loop that is really vague, that we don't know what is inside. Okay, I just use this to represent that. When do you think we can get out of the loop? If you just look at this example here, we start off with 71, we chop it down to 36, 18, 9, 3, and then finally 1. So when do you think we can exit and say, oh, we're all done, there's nothing else to do?
Want to get one?
Sorry, go ahead.
Number times 1.
When it is 1, okay, when we're down to 1, there's nothing to factor anymore. Okay, very good. So exit when the number to factor is 1, because there's nothing to do in that case. And we'll call it the first version of our program. Okay, this does not look like pseudocode at all. Right?
No.
So, version 2. Version 2 is saying, yeah, but the number to factor is 1 is really kind of confusing. Can we use a variable name to replace, quote unquote, the number to factor? Let's just call it n, okay? Because mathematicians like n, I like n too. Okay. So we'll just say in version 2, call, quote unquote, the number to factor n. Okay, nice, because now I can rewrite this